can wait for a few minutes. 2 minutes. Okay. Because it's recorded. So.
Ela vai, eu vi o pessoal, tanta risada. Olha, nossa, foi muito engraçado. Aí teve ontem, agora não lembro o que era da cena. Passei a hora que eu saí do bandejão, tinha um menino ruivo. Amiga ruiva! Ajuda aqui. Acho que é. Era ele? Acho que ele era assim. É, tinha duas pessoas de cabelo vermelho. Amiga ruiva! Conta aqui com a gente, vamos lá, essa coisa dos ruivos. Ai, amigo. Até animei, mas eu falei, foi com ninguém. Aí fica pra próxima. A próxima boa. É da Copa Fora. O que é isso? É de jogos, sabe? Tipo, interus, índio, né? Essas coisas. Daí eu acho que uma festa, premiações. Mas é temático, assim? É fantasia? E onde você é?
Good morning, ladies and gentlemen. Good morning. Good to see you today. Yeah, so we are kickstarting the program today, and we are happy to have Matheus here with us, and Matheus Marcus is going to present something about his doctoral research, and is here with his supervisor, Professor Veronica Lopez. So we want to generate some discussions after this, and we hope that we'll have a good time.
Okay, people, I want to introduce more or less the topics of Matheus' talks. He works in a specific kind of models associated with Markov chains, but using a specific kind of data, genomic data, in faster format. So this is a specific format that is very interesting to explore in terms of Markov chains. So a Markov chain, he will explain for us, but you consider in the Markov chain a memory in the process. So in the faster format, you are looking for the constitution of the DNA, and you are from left to right, concatenating bases, A, C, G, T, coming from the genetic alphabet. So the idea is to catch this behavior, and specific in the Plasmodium Vivax situation. So this is the idea of this presentation. So Matheus separated the presentation in several parts. One is explaining the model, the second is explaining the goal, the statistical goal, the third is the application. So it's in modules. Okay, thank you very much.
Good morning, everyone. I'm Matheus, and I'm going to present this paper that I wrote with Professor Veronica and Professor Jesus. Thank you, Professor Veronica and Professor Wally, for the introduction. And let's begin here. So first, the introduction and the motivation. Mitochondrial DNA has many uses in biomedicine. Right? It can be used as markers in population studies, and it's also very used to trace the evolutionary history of any organism, really, but in this specific case of Plasmodium Vivax, and finding its closest evolutionary organisms among the other Plasmodium species, for example, Falciparum and all the others. So one thing we know about DNA sequences is that they are statistically correlated. And so we can build many models to try to understand what is the probabilistic structure of the chain, of the DNA. And one of the most popular tools for this kind of thing is the use of Markov chains. Usually we don't use chains of order 1, but of higher orders, as I'm going to show you more details in the next slides. But when we use Markov chains of order higher than 1, we start to have a problem with the number of estimation parameters, because it grows exponentially. So the idea here is that Professor Veronica and Professor Jesus have written a paper in 2017 with a methodology for grouping states in the state space, so that we can reduce the number of estimating parameters, making the problem more tractable. And we can also find statistical similarity between groups of nucleotides, right, or groups of genes, depending on the size of the Markov chain. That we can see there's statistical similarity, and we can use it to fuel further research. And this paper introduces an algorithm that can later be expanded to cluster analysis, which is a form of unsupervised learning, right? Unsupervised machine learning in the context of AI. Right? So first, starting with the basics, the idea of a Markov chain is that we have a stochastic process that is a process that is where the variables are recorded in order of time, in the order that they happened, and there is a statistical dependence in this order. But the idea of a Markov chain is that the conditional probability of an event in the present time is dependent, in theory, of all the previous events, but in Markov chains we have a property that it only depends on the immediately previous realization of this random variable. Right? So this is the traditional Markov chain, and this is in equation 2. Is what we call a higher order Markov chain, where we expand the memory. So instead of looking only at the immediately previous realization, we look at a few more realizations of M more realizations, right? And this allows for a more complex dependence behavior, but this also comes at a cost, which is the number of estimating parameters, right? So assume that we have a Markov chain to explain how a DNA sequence works, and this chain is composed of 4 elements, right? The 4 nucleotides A, C, T, and G, right? So this is the alphabet. From an inferential perspective, the number of parameters to be estimated in a simple Markov chain, a Markov chain of order 1, is given by the cardinality of the alphabet times the cardinality of the alphabet minus 1, which in this case is 12, right? Because we have to calculate the transition probability from each state to each state, right? But since they have to add 1, we subtract 1 from there, right? But when we increase the order of the Markov chain, we also increase the number of parameters. So instead of being the cardinality of A times the cardinality minus 1, it becomes the cardinality of A elevated to the order M times the cardinality minus 1. So in order to have an idea of how this increase happens, right, we can look at this table. In a normal Markov chain with the DNA nucleotides and a memory of size 1, we only have 12 parameters. If we increase that to order 2, we have 48, order 3, 192, and so forth. And if we go to order 10, we are already in the order of millions. So that's a problem for estimation. Right? So the idea here is that we are going to introduce this concept of a minimal Markov model to partition the to partition the state space, right? So we must introduce some notation, right? So we have a discrete time order Markov chain xt in a finite alphabet A that is equal to the nucleotides. So let's assume that S is equal to A elevated to M is the state space. For example, for M equals 2, we have all the possible combinations of the 4 nucleotides. So AA, AC, AG, AT, etc. Right? So let xi be a realization of the stochastic process, and xm to xn be a string of consecutive realizations of this process, denoted by x from m to n. So the idea is exactly like Professor Veronica wrote there. So we are going to have a sequence of realizations, right? And we are going to look at some nucleotides that come before. So for example, this is like an order 8 chain here, right? So for each state in the alphabet and for each string, we can write the conditional probability with this notation, right? And now we define what are equivalent states, right? So 2 strings in S. So for example, this is a string, right? We say that 2 strings are equivalent if they have all the transition probabilities equal to each other. So for every possible state in the alphabet, the transition probabilities of 2 strings are equivalent if their transition probabilities are exactly the same, right? So this is equivalence. Now let's imagine that we have a partition of S that already has some parts, right? So the calligraphical L is a partition, and the normal L's are the parts. A part is composed of a union of states. So we say, for example, going back here, we say that AA and AC are equivalent. Let's suppose that we have this. So we can write a part L1 that's composed of AA and AC, right? So we can find the probability of an Li by adding the probability of the individual strings. And this is the joint probability. We can also have only the probability of Li, and with both of them we can define the conditional probability as usual, right? So we can, after that, define what is a good part and a good partition. So a good part is a part where all states are equivalent. That is, I did not make a mistake here, right? The two strings really were equivalent. I joined them in a part, and if that is true, that part is a good part. And a good partition is a partition where all parts are good parts. Okay, so the main objective of the methodology is to find the minimal good partition, which we are going to call the minimal Markov model, right? And this partition is defined by the equivalent relationship. That is, not only are all parts good, and this is a good partition, but also that if two states are in separate parts, it is because they have different transition probabilities at some point. Right, so that is what's the minimal partition, right? We joined every state that we possibly could that had the same probabilities, right? Now the number of parameters to be estimated falls drastically, normally, to the cardinality of the new partition times the cardinality of the alphabet minus 1. But of course, the reduction in the number of parameters depends on how many equivalent states we can find in the space state. Right? So we are going to do the estimation using countings, right? Let's begin with a sample from from 1 to n of the process. For example, a DNA sequence in the FASTA format, right? We have to define what is the memory that we want for the chain. Right? There is an heuristic for that, but it's only for the upper bound. So we can say that m must be less than, and then this formula here, right? So this is the upper bound. So we can make several models with several orders and see which one fits better, right? Within this bound. So we are going to do countings, as I said. So we are going to count the number of occurrences of every string in the state space, right? So this is this ns alpha is the number of times a string occurs, followed by each of the possibilities in the alphabet. So, for example, right, we are going to have in the DNA example, right, we will have a counting for example, AA followed by A, so AAA. Then we will have like a probability for AA followed by C, which would be AAC, and so forth, right? And for every possible string in that order, we have these countings, right? And we can add up all the elements in the line and find how many times that string occurs, right? So this is a hypothetical example to explain exactly how these countings are made. We can do the same for a part, right? So first we had the strings, which are the let's say non-grouped, and now we can group things in parts, right? And to group things in parts, we only have to add their countings, right? So the minimal good partition can be selected consistently using the BIC, the Bayesian information criteria. It is the partition over the space of all partitions that maximizes this equation here, equation 3. However, the partition space is very, very large. So we cannot test every single partition, calculate the BIC and see which one is the best. We need a strategy to do that, right? So what we are going to do, first some more definitions, right? Let's suppose we have a partition, and that partition is a good partition, right? We can add two states like this, right? We are going to add state I to state j, and we are going to add the counts, and then we are going to have a new partition that is the partition that is the partition before, but now I and j are the same. So we are going to remove I, remove j, and add ij, right? And as an asymptotic result, right? If the original partition is good, then the BIC of the new partition will be better than the BIC of the old partition if and only if the probabilities are the same. That is, they were equivalent, right? So we join things that we really should join because they had the same transition probabilities. right? And so this idea here allows for us to find the partitions in an iterative process, right? So we can further help this search by defining a metric here. And so this metric is given by this equation 4, and this really is a metric, right? It has all the necessary properties. It's non-negative, it's symmetric, and it follows the triangular inequality. So this distance here really is the key to everything, because not only is what's going to make the original algorithm, but it's also what's going to make it possible for us to use cluster analysis in the next few slides. Okay, so this is very important. So why did we define this distance? Because we can prove that if the distance is less than 1, the BIC of the old partition is smaller than the BIC of the new partition. That is, if the distance is less than 1, we should join parts, right? According to the BIC, asymptotically, right? So this result is valid asymptotically with a very large value of n, right? So now that we have defined all these things, we can use the metric in an iterative search and find the minimal good partition asymptotically, right? So if we assume that we have this minimal good partition, we can then find the maximum likelihood estimation in a very simple way, because it's just going to be the relative frequency of the parts in the minimal good partition. Okay, so now let's make the link to cluster analysis here. Right? The idea for the original algorithm is that we are going to calculate the distance between each string first, right? Each part. We are going to start with a partition that is composed of each string in a separate part. We are going to calculate the distance between all of them, and then see which is the minimal, and then which is the minimal distance between two parts, and then we are going to take these two parts and merge them, right? And then we are going to do this again, but with the distances from the new part added, and substituting the distance from I and j, or the original I and j, and we are going to do this in a process until we reach a distance that is greater than 1, and then we stop, right? And the metric can be interpreted as a distance, right? Which makes the above algorithm an example of agglomerative hierarchical clustering among the parts. So here's what we're going to do. We have the probabilities for transition states, and we are trying to group transition states. So we are going to use cluster analysis to find which groups should be joined, which groups have a stochastic similarity, which groups should be put together, and which groups have similar behavior. So that's the whole idea of the thing, right? And cluster analysis is related to AI and machine learning as a form of unsupervised machine learning, right? Because the main difference here is that in a supervised machine learning, we have a training set and a test set. But here, we do not have a training set, and we do not have a test set, because the data is not labeled. Instead, we are going to use an algorithm, and we are going to let the algorithm decide what's interesting here, right? We are not telling the algorithm what to do. We are not telling the algorithm what to look for. We are telling it what to do, obviously, but we are not telling it what to look for. We are simply applying the algorithm and saying, well, this interesting result appeared from the algorithm. That's why it's unsupervised. Right? The idea of hierarchical agglomerative clusterings is that the method begins with a data set of cardinality M and creates a sequence of partitions, right? From calligraphical L1 to calligraphical LM, which is the number of the cardinality of the data set, right? The parts, which were parts in the original idea of the Markov chain, now are going to be called clusters, and the partitions are called clusterings, right? In L1, the first partition, every element is a separate cluster, so it's exactly how we began the algorithm here. So each element is in a separate cluster, and in the final one, all elements are in the same cluster. And in each step, we join two parts according to some notion of distance. Of course, in this application, we are going to use the distance that was defined a few slides ago. And these unions are irrevocable. So that means that when two parts are joined, they will be in the same part for the rest of the process, right? So in order to implement this, we first calculate the distance matrix. That is, we calculate the distance between each pair of elements and put them in a matrix, right? So in the first step, it is very easy because we just find the minimal distance in the matrix and join them. But how we do the second step? Because now we have several elements and we have a cluster. We have two elements. So we have to define what is the distance between the cluster and not only the elements, between the cluster and the parts, and later in the following steps between several clusters, right? So we are going to do that by using linkages, right? Which are functions that are applied to distances in each cluster and determine the distance between clusters and not just points, right? So we can think of the metric that was defined as a linkage, right? And I'm going to discuss this in the next slide. So the usual linkages can be calculated with the Lens-Williams formula. So what are the usual linkages, right? There are several of them. And in R, for example, there are about 8 of them. And all of them can be calculated with the Lens-Williams formula, which is given by this relation here, right? And the idea is that the new distance matrix can be constructed entirely from the distance matrix in the previous step. So once you have the distance matrix, you don't need anything else. However, in the algorithm that was presented a few slides ago, which is called algorithm 2 in the paper, right? We cannot do that. We have to return to the matrix with the countings, and then we put this in the distance matrix and do it again, right? So the first algorithm does not use this formula. However, with this formula and with the distances, we can use our metric with any type of agglomerative clustering. So single linkage, complete linkage, McVitie, average linkage, and all those, right? And the interesting thing is that the result of equation 6, which is the asymptotic consistency using the VIC, holds for any clustering method that is based on distances, right? And it continues having the value 1, okay? Even though the algorithm 2 cannot be represented by the Lens-Williams formula, it can be thought of as a linkage. And so we can do what we usually do in cluster analysis, which is to create a dendrogram and use cutoff points in the dendrogram to find a partition. So even though we originally are using 1, we can use any value, right? That's going to give us it's going to give us a partition. Once we create the partitions, we have metrics to measure the cluster quality in terms of similarity of the members to each other and in relation to other parts, right? So first we have an internal quality measure, which is called the average silhouette width. That's an index that goes from -1 to 1. If the values are negative, the clustering is bad. If the values are positive, there is a cluster structure there, right? Because this measures the similarity of indexes that are in the same cluster in relation to elements that are outside the cluster. And so this is an internal quality measure. We also have measures that simply measure the similarity between two clusterings. Not clusters, clusterings, right? Two algorithms, it measures the similarity of the clusters created by the algorithms. And so we have 3 here, the Fox-Mallows index, the adjusted R index, and the Mela-Heckermann index. The Fox-Mallows index is very useful for simulation studies because it allows, it's possible to break it into separate cases, and this is very interesting for simulated data. The adjusted rand index is the most common in literature, and the Miller-Heckermann index is interesting because it also gives us which pairs of clusters are the most similar to each other. So it's going to say cluster 1 from this methodology is the most similar to cluster 3 of this other methodology, right? We have conducted simulation studies, right? And the idea is that the partitions created by algorithm 2 are the most similar among the traditional cluster methods to the partitions created by Ward's method. And Ward's method can be represented by the Lens-Williams formula, and these are the parameters, right? And also in the same simulation studies, we have seen that the two best methods for recovering an original structure that was a partition model were exactly Ward's method and algorithm 2. Right? But of course, these are simulations that assume that the real model is partition model. Right? So with this, we can go to our application, right? Which is the application to mitochondrial DNA. So we have a sample from mitochondrial DNA of Plasmodium Vivax called AY598074. This was collected in Brazil, and it was presented in this 2005 paper. It is available online here in the FASTA format. It contains 5,919 nucleotides. So first, we can look at the relative frequency of all the nucleotides present. And so this is more or less it. So if we were not going to use any model, we could say that transition probabilities are this. But of course, we're not just doing the technical things, we're applying the model. So we apply algorithm 2 and Ward's method to this database, and we select for this analysis an order m equals to 3. Right? So the result was that algorithm 2 partitioned the data in 5 clusters and Ward's method in 3. Right? And those indexes that I previously mentioned, right? Algorithm 2 had a silhouette value of 0.36, Ward's method had one of 0.32, and the Fox-Mallox index was 0.59, adjusted R index was 0.4, and the Miller-Heckermann was 0.625, right? And these indexes, last indexes, they all go to 1, right? If it is 1, the partitions created are exactly the same, right? And the idea here is that the silhouette index is slightly better for algorithm 2, but we have a value between 0.25 and 5, which suggests that there is room for improvement. And the idea here is that probably the sample size was too small, because not too small, but it was small, because it was only 6,000. If we, for example, expand this study to incorporate more samples, right? So we are using this with a single sample, right? If we add the countings of several samples of mitochondrial DNA, we are going to have a larger sample size, and probably we are going to improve the silhouette index, right? So the similarity index that all go to 1 show that the results are different, but we are going to interpret exactly how different are they, right? So the following table gives us the cluster memberships. So here we have the 5 clusters that were created by algorithm 2 and the 3 clusters that were created by Ward's method, right? So we are in an order 3, so we have 64 transition states, and they are all here with this idea. And this is the correspondence there is given by the Miller-Heckermann. So for example, M2 is correspondent to, is the most similar to W2, right? And there is one case which is W3 and M4, which they are exactly the same. So the 2 methodologies created the same cluster here. Right? And with these clusters, we can do the estimation. So these are the transition probabilities calculated using both partitions, right? So notice that originally, if we are using an order 3, we are going to have 192 parameters to be estimated. With algorithm 2, now we have only 5 groups, so it falls to 15. And with word, we have 9. We have 3, so the number of parameters is 9. So from 192 to 15 and 9 is a very large reduction of the number of parameters to be estimated. So here's the dendrogram, right? If you're not familiar with the dendrogram, the idea is that each point here is a transition state, and this value on the y-axis is the value of the metric when they were joined. So we can see that most of the merges, almost all merges, happen between the values of 0 and 1, which are highlighted in both graphs. And this happens both for the partition model and Ward's method. So we can see here that Ward's method had 3 clusters, right? And here PMM had 5. So in the next slide, I'm going to show it in more detail. Okay? And it's interesting to see that for further agglomerations, right, for further merges, we were going to start to have to improve a lot the value of the height. A lot for the PMM and more or less for the Ward's method. Right, so these are the partitions created, and these are the transition states, right? So here is GAC, GCA, etc. Right, and the heights in which they are being merged. So in this gray box, we can see that this is M1, that is M2, M3, M4, and M5. And the same thing for Ward's method. They are not in the same order here, because it is impossible to do the dendrograms in the same order if they are different partitions, and they are different partitions, so they are not in the same order, but we can clearly see the states that are being grouped and at which heights they are being joined, right? So for example, if we reduce the height here to about here, it's probably 0.8, we are going to have this W1 be split one cluster here and another cluster here, right? And if in turn we increase the height until about here, those W2 and W3 would also merge, right? So that's the idea of the height values. And again, we have chosen the value of 1, because we know that with a large enough sample, the value of 1 will select the minimal partition, or that is the correct partition according to this methodology. Right? We can also directly cross both clusterings and see the common elements. So for example, these transition states, ATG, CAA, CAG, CAT, etc., are 10 states that are in M1 and in W1. And so these are 10 of 12 of M1. But what happened to the 2 that are left? The 2 that are left go to that are in M1 go to W2, right? And we can do this for all the clusterings. So we can see a pattern here that M3 is a bit different, but all the others are all the other clusterings created by algorithm 2 are in the same cluster in Ward's method. So first we have 2 identical parts, as I said before, which are M4 and W3. The 9 elements that are in this cluster were created by both methodologies. And then the other one is that M2 is contained entirely in W2, and M1 and M5 are almost entirely in W1. There are 3 states of M1 and M5 that are not in W1. And M3 is more or less split evenly between W1 and W2. Right? So, what are the conclusions here? Well, Markov chains can be used in DNA studies to characterize the stochastic structure of data. Markov chains of order higher than 1 are used frequently in this task, but the number of estimation parameters grows exponentially as you increase the order. We can use the partition Markov chains to group states in equivalent classes, which can give us characterizations of the data structure. So, for example, we can have an idea that these transition states or these sequences of nucleotides have something in common because they have the same transition probabilities. So we can investigate if there is any reason in biomedicine or in genetic that these these sequences of genes are similar, or if they are associated with the same proteins or things like that. So this is the machine learning part, right? Because it says that these elements are similar. So then we can try to understand why they were classified as similar. So that's the idea of unsupervised learning, right? You have data and the algorithm groups the data, and then you see, well, why did the algorithm group the data? What was common between them, right? So that's how we use cluster analysis in this problem. Well, so that's how it characterizes the data structure, and it also reduces the number of estimating parameters in the model, right? So the metric defined in 6 can be used to asymptotically find the minimal good partition, as well as introduces the possibility of distance-based clustering methods, such as agglomerative hierarchical methods, which are a type of unsupervised machine learning. Applying the results of algorithm 2 and Ward's method to mitochondrial DNA of a sample of Plasmodium Vivax, we could reduce the number of estimating parameters from 192 to 15 and 9 respectively, and we have shown several similarities among groups of nucleotides, right? So, for example, this last sequence, which is the cluster that was generated by both methods, right? So, that's it. So these are my references, and I know that it was a bit fast, it was a lot of information, so since we have time, we can have questions, and I can review some of the parts here. If someone wants a more clear idea, or to explain a bit more of the indexes or of anything else here. So thank you very much, and that's it.
Thank you, Matheus. Any question or comment?
Well, thank you so much for your presentation. It's a bit, of course, very complex for somebody like me, but I would like to understand the application in medicine, in research, I mean malaria research.
Yes, so the application is, we can have many applications, but the idea is to find similarities between nucleotides. So if the nucleotides have a similar behavior, we can infer that they are associated with similar things, right? So that's one of the ideas. And the other one, was done not in this paper, but in another paper, right? We can take 2 different strains of an organism and see the partitions that they generate, and we see if the partitions are the same. So if the partitions are the same, we can say that there is a probabilistic similarity between these 2 populations. So we can try to understand why is that. So this is more like a tool to indicate interesting connections for the researchers in biomedicine to further explore with other types of techniques. Right, so that's more or less the idea.
Let me add something. Suppose you have several sequences of Vivax,
Okay.
and you want to decide which of them is the most representative of Vivax. You have a natural variability. Sequences in the FASTA format. Suppose you want to identify a goal pattern sequences in order to compare these goal pattern, these goal sequences with others. This happened, for example, in Epstein-Barr virus. The people use all the time one that was coded in 1978 or 6, something like that. It's corrected all the time. So they use to compare new sequences in order to identify mutations inside. So, for example, we used also this kind of model in order to see the connection between virus and cancer. Recently, we used it because you have some specific mutations, and you can see the change in the frequencies of occurrences. So, for example, here we can see if this Vivax is near or very far away from another, suppose between different countries. You can compare the homogeneity in this kind of behavior. For example, put the slide of the partitions. Here we have two methods, but this model, the minimal Markov model, say that all these combinations share the transition probability from another element. So the chance of be together to A, be together with T, and all these properties change when you do some intervention in the sequence. For example, a cancer, or for example some kind of specific mutation inside the DNA structure. So the idea is to create a profile of this sequence, or a way to rescue a profile. This is the idea. Of course, we have several methods. This is an example that achieve different answers. So we need to improve, increasing the sample size, for example, taking several Vivax sequences and producing a more confident results. But we did this because your presence here. We started to work with Vivax now. So the idea is to compare to identify mutations that produce change in the probability to have three elements, ATG, going to choose as the next element A or T or C. For example, here, this is the next element. You have AAC, and the next element is G. So we want to compute the chance to do that, to the sequences to produce this junction. Because when you have an intervention or a mutation, you can remove G and put another thing. And this produces a mutation in the DNA sequence. This is the idea. And we have several methods to achieve the groups, to obtain the groups.
And we could, for example, do the same thing with Plasmodium falciparum and see if the transition, if the cluster created here is the same with the cluster created there. And then, if they are not, we can see where are the gene differences between these two types of malaria, for example.
Thank you.
Some question, comment?
Thank you so much, Matheus, for this. It's a very interesting talk, and it really adds color to this workshop. It's very applicable. Yeah, so, but I want to suggest that you consider DB scan. Have you heard of DB scan?
I have heard of DB scan. We haven't applied it to this type of data.
You applied it?
No, we haven't yet applied it.
Yeah.
I have heard it.
Density-based spatial clustering or of applications with noise. So it can identify on noise in your data set, and it's good, it's scalable for large and complex data sets like the one you are considering, and it can identify rare mutations. Yeah. So probably you should start from K-means, compare the results you have with that of K-means. Have you tried K-means?
Yes, that's a good question. I have used K-medoids, but for k-means, the problem is that the mean of this distance is not yet well defined. So it is difficult to apply k-means. So I'm trying to work out how a mean work in this type of metric, because they are non-Euclidean.
Yes.
So first we are going to have to define the means and then use the k-means. The k-methods is possible.
Okay, you use Manhattan distance?
No. It's
not
that
Euclidean.
distance it's non-Euclidean.
Okay.
It's this distance here is given by this equation.
Okay.
It's a new distance.
Oh, it's a new one, you designed it?
The Professor Veronica and Professor Jesus did.
Very good.
So it's non-Euclidean, so that's the problem with using the traditional model-based clustering, right? But it is, yeah, that's a next step.
Yeah, an advanced method.
Yes.
Thank you for the question, Olawale. I will explain why we use this distance and not the others. Because we created the model. We created a model that is with the purpose of producing these clusters. Okay, we need to find a way to identify the elements that are together or not. But using what principle? The principle is that you need to obtain a partition that is optimal in some way. Optimal in some way. And the optimality of this partition is achieved through the Bayesian information criterion in this model. Why? Because previous works in the area, in stochastic processes, for example in 2006 and early, used the Bayesian information criterion to estimate consistently some specific structures. Consistently means that when you increase the sample size, you obtain better and better results. You achieve under a specific hypothesis, you achieve the through model. Exactly, it's something that you can prove in a mathematical way. So we decided to use, we proposed the model and we decided to use the Bayesian information criterion to achieve a good estimation. And using the Bayesian information criterion, when you open the Bayesian information criterion, this expression of the Bayesian information criterion, so if you look at this, you need to maximize this expression. The partition the best partition, the best L, need to be the one that maximizes this criterion. This is model selection theory. This is model selection theory. And to do that, you need to run all the possible partitions. That is a huge quantity of partition. So you need to have a strategy to do that. So looking at that, we decided to investigate the Bayesian information criterion, theoretically, in order to bring for us a techniques or a metric that allow to produce the best estimation. So we open this expression and we obtained the metric. Please go to the metric. This metric that says some clusters need to be separated or need to be together. One versus the other. Some parts need to be separated or need to be together. How we decide? The BIC increase. When the BIC increase is a number, when the BIC increase, the option is put together. When the BIC decrease, separate. So this is the metric. It's a metric in the mathematical sense that we created, and Diego is extending this notion. Diego is also my student. So we created this and proposed an algorithm, very initial algorithm. So Matheus is working in comparing different algorithms in order to see if he can improve that algorithm or maybe classify the algorithm. That is something that we never do. We never did. So I think that the real question here is how to use this metric in the concept of clusters analysis, as Matheus do now.
Because hierarchical clusterings are the first step, right? Because they are the most simple clustering structure. So the next step is to go to model-based clustering. Yes, which include the BTB scale. So that's on the roadmap.
What are the constraints of your metric?
Sorry,
in which sense?
constraints?
Yes.
This matrix is operating. Suppose you start with all the states separated. The states are show me the states, the state space. Sorry. In the case of the
this is the state space because it's all the
yeah, all the combination of these letters A, C, yeah, all the combination of three elements. You start your process with all those elements separated, and you start to measuring by the first two, or all the pairs. You compare all the pairs. Okay, I compare the distance between two elements, these two, these other two, all. And you extract the inferior distance, the lesser value. So if the lesser value is inferior to 1, they need to be put together.
Is there a specific formula for the permutation of the comparison?
The idea of all algorithm 2, the initial algorithm is this. You compute all the comparisons. I and J are the triples. You compare all, and you identify the index of those that is the inferior one. So if this index is inferior, if this number is inferior to 1, you need to put together, and you start the process again. But you have several ways to do that. So this is the real problem. How you to do what methods, complete linkage, simple linkage. So this algorithm appears looking just for the metric, but you have several ways to do that. So our idea is to collaborate with clustering methods to be introduced in other kind of techniques. Now, we can look for this metric and we can amplify the possibilities. You can change the metrics using another criterion, for example, the EDC criterion, the efficient determination criterion. We did this 3 months ago. Or you can use a new metric to measure samples. Suppose you need to decide if 2 samples of the Vivax are relatively near or not. That is Diego works.
It's work in progress.
Exactly.
Yes,
Exactly. Sorry for the complexity, but
So let's applaud them. Thank you for the talk. If there's no other comment, I think we can go for our tea break. It was such an interesting session. Thank you, everyone. So, announcements. If you need certificates, please put down your name. See Douglas. Douglas will be around. If you want to have your certificate before you go, please write down your name legibly before you go. Right? Legibly. And otherwise, we will send to you via email.
yeah.
But if you want to get it today, please write it now. Okay? And second announcement, there will be quiz in the afternoon. Quiz, multiple choice question for the students. Yes, yes. So please prepare for that. Like 25 questions. Yes, multiple choice. Before the presentation. Yes, it's like a first course, you know, before you now present. So please, third announcement, the presentations were held today by the participants. So we want to listen to you, and we want this to generate more insights. Probably you can even develop some of these concepts into a research paper in the future, especially among the undergraduate students. Okay? So please do put as much as possible into your work, and we are going to have your reports you submit to us. Then we can follow up on that and mentor you further. Is that okay? So thank you so much. Let's come back. We are going to the other side after the tea break. Okay. Thank you. Please, a round of applause for yourselves.